let's make sure ANSYS has the right set of governing equations. If I go to the slides that I used before, we saw that our governing equations were the differential equations of equilibrium, which specify that each infinite small chunk has to be in equilibrium, and we had zero body forces. And then to express these in terms of the displacements, we bring in the 3D Hooke's law and the strain displacement relations for small displacements. Now, if I go back to the project page in ANSYS, it uses two clues. So it says, oh, you're solving a static structural problem, and also we have given it, under geometry, we have given it a volume. And it uses these two clues and says, hey, you know what? I know you want to solve the 3D equations of differential equations of equilibrium. And this is true even if you have multiple volumes. So using those two clues, what it's done is it's turned on those equations with zero body forces, which is what we want. It's turned on the Hooke's law with some default values of E and nu, which we will go check. And it's turned on those equations. So it has a set of equations that we want. There are no constants here. We have zero body forces here. And here in the 3D Hooke's law, we have two constants. And we want to make sure it has the right values. Now, in the problem, we are given only the shear modulus, G, which is 78 gigapascals. But really, we want two constants, E and nu. And these are related to among themselves in this way. And if you have not seen this before, you can go to my course on EDX, Hands-on Introduction to Engineering Simulations, and look at the Big Ideas, Section 2.1, Big Ideas in Solid Mechanics. Okay, and we will specify nu to be 0.3, which is a common value for the Poisson's ratio, and then we can calculate what E is, and it comes out to be 202.8 gigapascals. Really, the problem should have given us two constants. It gives us only the shear modulus because in the analytical solution, you assume that it's a pure shear state, and so only the shear modulus affects it. Okay, so let's go and check what the default values of E and nu are in ANSYS. So I can do that. To see what the default values are, I go to the mechanical window, and if I expand geometry and look under sys solid, I see that the material assignment is structural steel. So essentially it's using E and nu for structural steel. And if I go and check what that is, so I'll go back to the project page, and I will right click and say edit. That opens up a new tab. And for structural steel, you see the Young's modulus is 200 gigapascals, very close. The Poisson's ratio is what we have. And you see the shear modulus is 77 gigapascals. Now at this point, you can say, you know what, there's at least, there's like a 10% variation in material properties in commercial samples. So that's good enough. I'll just use the default values. And that's what probably is, about what I would do. But here I want to show you if you want to define a new material, how you do that. So I'll go here and I'll say where it says click here to add a new material. I'll click there and I will give a material name. I'll just say go big red from a material name, big red being Cornell, and then the material is going to use isotropic elasticity, and if I drag that on here, I'll get a space where I can define the Young's modulus and Poisson's ratio. So the Young's modulus is 202.8 e to the power of 9 pascals, and the Poisson ratio is 0.3. And you see that the shear modulus comes out to be 78 gigapascals, which is what we want. And then if I go to the project tab, it says, hey, you've made some changes upstream. Do you want it to propagate downstream? So I will right-click on model and say refresh. And now if I come back here, I should be able to select Go Big Red. So then it has, so now it has E equal to 202.8 gigapascals, and it has nu equals 0.3, and we also saw it's turned on the equilibrium equations in the form that we want with zero body forces, and then it's turned on the additional relations to write that in terms of the displacement. So the Hooke's law, the 3D Hooke's law, plus the strain displacement relations. So we are good to go in terms of the governing equations. Let's move on to specifying the boundary conditions.